Good. Welcome back, everybody. Let me just take in-class attendance, in which I have no clue why am I doing this.
I think you know us.
Yeah, you don't need to do that. Just say we're all here.
See, I'm doing this to make up for all the times I didn't in Arrow.
Oh, I did.
Well, basically, I'm taking this attendance because school taught me to do. If somebody gets sick, they probably, try to track out like who was sitting next to you, kind of thing. Okay. So that's probably the only purpose. But anyway, so let's just continue on this example. Okay. Example C23, page 1, page 2, range and endurance. This is the real data T38. By the way, you can actually download this data very easily. Let me just take a look at it. Okay. Go to website, AE317, go to course materials, and you can actually download handout. Okay. Where's the handout? Yeah, this one. Handout C1A. This is T38 data, complete set of data. So this is T38 performance data. Okay, so you can actually download everything.
Wow.
So this is airframe dimensions and engine power plant. Okay, then this is engine ratings, and this is, what's this? What's this? This is CO alpha. Here we go. CO alpha with the flaps 4 down, flaps 20, flaps up. Huh? What? Yeah. There's a small accident in classroom. Are you drinking like what is that, the guacamole or something?
Oh my gosh.
It looks green. Or avocado like that.
Drinking.
Or green tea, I don't know.
Guacamole. It reminds me of that song.
And then he spilled the green tea. Okay, anyways. So yeah, this is CO alpha prod with different configuration, right? What's this? What's this prod?
I can't.
Mach versus zero.
Yeah.
Zero lift drag coefficient, what is it? CDO. So this is hyping up Y. This is a wave drag addition. So if you go across like a transonic to supersonic, you're going to add a wave drag component to the CDO, which is parasite. Okay. All right. How about this? Ooh, what the heck is that? Drag due to lift, which is induced drag, plotted against Mach number, which you see the transition. Here's a transonic flow. Okay. Oh, here we go. This is the thrust plot. Okay, this is the sea level thrust available. This is the military power. This is the maximum means afterburner on. So this is a dry and wet. Okay, and here is the drag, which is the thrust required for a given different airplane weight: 12,000, 10,000, 8,000 pounds. And then you have a similar plot. This is 10,000 feet altitude. This is the 20,000 feet altitude. This is the 30,000 feet altitude. This is 40,000 feet altitude. This is what, 50,000 altitude. So with a different altitude, you have a thrust plot. This is the power plot. This is the sea level power plot. This is the 10,000 power plot. This is the BN diagram. We're going to cover that later. Okay. This one too. This is the, what the heck is that? This is the maneuverability plot. We're also going to cover that. Okay. What is the minimum rate of turn radius and stuff like that? We're going to cover this too. So this is the entire sets of actual data of T38. So I think the easy way to make an exam is, okay, here's the data set, go ahead and use it, and then I give you a series of questions. Read off from the data chart. That's it. It's very simple exam. I don't have to do anything. Okay. So so let's be ready for it, because that's something you really want to develop as a skill set. Okay. All right. So let's just continue on. Example C23. So you're flying T-38 standard sea level condition. Your aircraft weighs 12,000 pounds. Answer the following. So we looked at a few things in last class. So I think we did the first 5 questions. First 5 questions. Fifth one is that what Mach number should you fly for minimum power of sink rate? Obviously, minimum power of sink rate is right here, minimum drag point, 0.41 Mach number. Then can you actually compute minimum sink rate itself? Now you are going to switch over to this one. Okay, so this is the question 6. Here we go. What is the minimum sink rate? Minimum sink rate equation is basically what is it? The minimum power required. But you need a power. You need to read off the minimum power required divided by weight of the airplane. So you need to switch over to the power plot. So this is the power plot. Okay. So this is the minimum power required point. You're going to read off the minimum power required divided by the weight, 12,000 pounds. That is going to give you minimum sink rate. Okay. Take a look at this. This is the minimum sink rate. So reading off the value here, what is the value, by the way? Can you get the value here? So corresponding here, well, a little bit below 0.5 times 10 to 6. It's like a little bit less than 500,000 foot-pound per second. Right? Okay. You see that? So the textbook actually chose 450,000. A little bit below 500,000. 450,000 foot-pound per second, and then you just plug in. This is the minimum power required divided by the weight of the airplane, gets you 37.5 feet per second minimum sink rate. Okay, makes sense. So hopefully you can compute those things by just giving you this data. Okay, problem 7. All right, let me just erase this. Okay, by the way, this is going to probably be most likely on exam 2. So, important discussion, all right? So, number 7, at what Mach number should you fly for maximum angle of climb with military thrust no afterburner at this altitude? So, what is going to make you maximum angle of climb? What is the condition? Maximum climb angle. So you are going to take a look at the power plot. Here we go. Maximum climb angle. Maximum climb angle is, well, this is thrust, right? So again, once again, same thing. Maximum climb angle, well, that's a climb rate. Here we go. Okay, here's a confusion. Climb rate and climb angle is different. Climb rate, yes. You need to have a maximum excess power, but climb angle not. So maximum climb angle is once again minimum drag right here. For 12,000 pounds airplane, this is going to be a maximum best military thrust angle of climb. Mach number is once again 0.41, right? Okay. And then question is, so what is the corresponding maximum angle of climb? That's question 8. So maximum angle of climb, let me just zoom right in. What is your maximum angle of climb? So this is the condition of maximum angle of climb, okay? This is Mach number 0.41, minimum drag point. Okay, once this is given, you're going to find out the flight path angle, which is inverse sine of thrust minus drag divided by weight. So thrust minus drag. Drag is minimum. Drag is minimum, 1,000 pounds. So at that minimum location with the military thrust, what is the available thrust? Let's just take a look at it. So you're going to take a look at it. what is the available value of the thrust, which is right here. So this is 1,000. This is like 4,250. Yeah, 4,250. Okay, pounds. So that's right. 4,250 pounds thrust available. Subtracted thrust required or drag 1,000 pounds. This is a minimum value divided by weight of the airplane taking inverse of sine. This is going to give you the maximum angle of climb, 15.7 degrees. Here we go. Get that? Now, confusing enough, next question is, so what is the maximum rate of climb? Not the angle. Here we go. So what is the rate of climb? What is the condition of maximum rate of climb? I think David knows already. We are going to take a look at the power problem right here. In order to have maximum rate of climb, you need to have a maximum excess power. So that is, what is the maximum gap between military power against, this is the power required. This is the power available. This is power required. So in order to find out maximum excess power, you are going to draw a straight line parallel to the power available line. This is almost straight. It's not quite, but it's almost straight. That straight line is shifted, and touching the power required curve right here. So this is going to be the maximum excess power your airplane can have. This is max excess power. In other words, power available minus power required, excess power. Okay. This is the condition for maximum rate of climb. What is the Mach number? 0. Not quite 0.7. 0.67. Huh? 0.67. Something like that. Okay, good. So this is the flight condition for maximum rate of climb right here. Here we go. And then what is that value of maximum rate of climb anyways? Let's just find out. The equation wise, oops, I just keep clicking the wrong thing. Okay, so this is the condition of maximum rate of climb, Mach number 0.67. So what is the maximum rate of climb corresponding to it? You are going to find out the excess power. Excess power can be read off from the chart at the Mach number 0.67, okay? So that means, here we go. So maximum excess power. So this is the power available. What's the value? This is like a 250,000 foot-pound per second. Okay. This is power required is about a little bit more than 1 times 10 to 6 foot-pound per second. Okay. So those two values need to be read off from this chart. Okay. And then plugged into the equation. Equation is, this is the equation. Okay. So 3,500,000 minus 1,350,000 foot-pound per second. This is the excess power divided by the weight of the airplane, which is 12,000 pounds. It's going to give you the maximum rate of climb, 9,500 feet per minute. Okay, this is still powerful, very powerful airplane. How's that? Okay, next question is, question is getting more confusing. Oh, this is quite confusing. This is going to be a fairly challenging question. Definitely something I want to cut and paste and make an exam question. You know, because it's so easy. Now, you climb T-38 to 20,000 feet and level off. Assume standard 20,000 feet atmospheric condition. The aircraft now weighs 11,000 pounds, and you have 2,000 pounds of usable fuel. What do you mean by that? At the beginning, you have 11,000 pounds of airplane weight, including fuel. But at the very end, after you consume all the fuel, you have 9,000 pounds of weight. So what is the average weight? 10,000. Okay. So this is 10,000 pounds average. You're going to use the average method for range and endurance. That's the easier equation, not the brigade equation. That's why you need to come up with average weight, okay, of your airplane. All right. Go ahead. Question.
On an exam, would
Yeah.
you be using the average value or the actual equation?
You can use either, depending on what kind of information you're going to get. Okay. Yeah. I will probably say use the easier equation than brigade equation. Okay. And this is absolutely necessary. Okay, so this is a 10,000 pound average. The reason why I'm doing this is because we have a 10,000 pound weight airplane performance data, which is product. Okay. And what is your maximum range at this altitude if you use all of your usable fuel to cruise T-38 military power? TSFC at the sea level is given. So you have to come up with a TSFC sea level to convert it to TSFC at 20,000 feet, right? Of course, you have to do that. And then question 12 is, what is your maximum endurance at this altitude if you use all of your usable fuel to loiter? Well, those two are quite interesting questions. Let's just take a look at it. Okay. Loiter means endurance. Yeah, this is endurance. So this is maximum endurance. This is the maximum range. Those are different. Okay, conditions different. Okay, so let's just take a look at. So this is a 20,000 feet data. Here we go. So 20,000 feet data, you are actually now using the average airplane weight. So you're going to track this line, 10,000 pounds of airplane, 10,000 pounds average weight. Okay. How's that? So you're going to use this plot data. So this is the power required at the altitude 20,000 feet. Okay, this is quite important. So what is the condition for, let's begin with maximum endurance to begin with. Maximum endurance, what is the condition for that? In order to maximize the endurance, you really want to fly with the minimum power required, isn't it? Minimum power. That's going to maximize the endurance. Now, maximum range, you have to fly faster than that. You remember? So, maximum endurance, you simply picked up this curve right here. This is the minimum power required, which maximize the endurance. Okay, maximize the endurance. In order to maximize the range, you are going to draw a tangential line starting from the origin. That straight line touches this curve, which is slightly higher by. Where is it? I have to zoom in. Where is it? So this line touches this 10,000 pound line. Well, it's about here. Here we go. So those two are different. This is endurance max. This is range max. Maximum range condition is always faster than maximum endurance condition. Let's be careful. So those two actually making a slight difference. One is slower Mach number, lower Mach number. One is higher Mach number. One maximize endurance, one maximize range. And then you're going to read off the corresponding value, which is fairly close, but this is the required drag value. Okay. So having said that, we are going to pick up the range and then endurance equation. So let's just take a look at here. So what is your maximum range? Okay. So first of all, maximum range you are going to have Mach number 0.61 and then maximum endurance. Okay. Maximum endurance is low. What is maximum endurance? It doesn't say anything. This is 11, right?
It's right below it.
Right below it. Right below its maximum endurance. What is the condition for that? 0.41? No, it's not.
Would it be for minimum drag?
That's a minimum drag, that's right. What's the Mach number?
Wait, I had a question. On the graph above,
Yeah.
why did you use not? Wouldn't it be 4.41 when you use the?
Well, that's the sea level. We are now 20,000 feet.
Oh, okay.
Yeah, so it's slightly different. So let me just take a look once again. Okay, so this is the minimum drag for 10,000 pounds. Yeah, of course, the airplane weight is different. We are using average weight, and also this is a different altitude. So Mach number is different. So let's read off here. This is what 0. No, this is 0.5 something. So this is 0.5.
No, that's
0.54. Yeah. And then here, this is the maximum range 0.6. 62, 61, 62, something like that. What is the actual value? 0.61, yeah? Yeah, 0.61, okay. So this is the maximum range. And then maximum endurance, this is 0.54, okay. This is the endurance max. 5.3, 5.4, something like that, right? Okay, so let's just take a look at the range first, okay? So you're going to, of course, use the range equation. This is average value method. So the range for average value. Average value method, okay? So this is going to be, you're going to use the TSFC at the 20,000 feet value. Drag average value is going to be given. How do you get the drag average value? This is a delta WF. This is 2,000 pounds. In other words, this is the 2,000 pounds of fuel you're going to use up all. Okay, so this is given. Velocity, wow, velocity. You need to multiply actual speed of sound times Mach number of range max condition to get you here. This is the velocity. You can get that. This is the TSFC at the 20,000 feet. Yes, you can get that. So drag average. How do you get drag average? The average drag for cruise is 950 pounds. You just read off about it. There we go. So this is the drag. Yeah, okay. So drag value is this value. Okay. Yeah, so that's the drag value. You read off from the chart, 950. Okay. So you just plug in all of those values into the equation. Then this is going to be the maximum range. Here we go. Okay. And then obviously 11 and 12 are very closely related. However, the condition is different. Maximum endurance, you're going to choose the minimum power point. Okay. So the drag value is a little bit different. Okay. It's a slightly lower value than the maximum range case. So maximum endurance, drag is slightly lower because the condition Mach number for maximum endurance is different. Okay. Are you with me?
Yeah, sort of.
I can tell. Okay, repeatedly. This could be on exam. Can you handle?
It's a little crazy right now.
Yeah, I hope so. Okay, so be very careful. You are going to read off two different values of drag. One is, of course, this value for maximum range, this value for maximum endurance. Obviously, one is for minimum drag. One is minimum drag. This is not the minimum drag, okay? Because in range, you fly faster, okay? So anyways, any question here? So this is a maximum endurance, 2.25 hour if you fly 0.54 Mach number. Question? So like I said, this is going to be very easy exam. I can create it like spending 10 minutes, cut and paste. Okay, bunch of questions. Can you handle that? So this actually requires a solid understanding what is range and what is endurance. This is actually fairly challenging thing. And then, not to mention that this is only for turbojet. Uh-oh. Uh-oh.
Wow.
Now today we're gonna talk about propeller-driven airplane, which is completely different. Which is different. Okay. So prepare. Okay, like I said, prepare to be confused. This is confusing. This is basically turbojet, turbofan engine only. All right, which is already different from sailplane. You looked at the sailplane to begin with, okay? If you look at the sailplane, you can determine minimum sink rate and also maximum glide range. That is essentially range and endurance. Range and endurance of sailplane is different for this case. This is the case for turbojet to turbofan, range and endurance. Now today we are going to take a look at propeller airplane range and endurance, which is different. Let's take a look. Okay, so now I'm going to go back to the regular mode. Okay. Let's continue example C24, which is one more example to finish up this turbojet turbofan thing. Okay. A turbojet powered trainer aircraft such as T-38, you've looked at it. Weight is 5,000 pounds and is flying at 25,000 feet with 1,000 pounds of fuel on board. Its drag power is a CD, which is given, CDO plus K times CL square. Its wing area is given, and the TSFC of its engine is 1 per hour at sea level. What is its maximum range and endurance to tanks dry? That means you use up all the fuel of 1,000 pounds at this altitude, 25,000 feet. And what speed should the pilot initially fly to achieve each? Okay, before we begin doing this example problem, okay, you really need to remind yourself, okay, stay focused. This is only for turbojet. Do not do the same thing if it's propeller airplane. Okay? If you do such a thing, you could possibly be getting 0 out of 10 in exam because you're doing completely wrong thing. Right? There's a danger here. This is turbojet. This is turbojet. Turbo. I have a tendency turbojet and low bypass turbofan.
Wait, only low bypass turbofan?
High bypass is okay. In other words, turboprop is considered propeller-driven airplane. Yeah. Okay. Anyways, turbojet, turbofan. Okay. Bypass ratio comes into play if you really want to get into the fuel consumption, but we're not going to talk about it.
That's probably for us, Matthew, since we're doing ultra long range.
Well, yeah, you need to come up with the engine spec, which is more accurate value. That's going to come into play on your, analysis. Okay. Anyways, that's right. So make sure you have a very detailed catalog spec installed, thrust and TSFC and all that. Okay, in order to accurately analyze your airplane. Okay, because that's going to have a huge impact on your performance. of course, range and crime rate and other things. Okay, so let's just take a look at it. Maximum endurance. What's the condition? Minimum drag. Minimum drag. Or oftentimes we can say this is width to drag ratio maximum, right? It's the same meaning. Or, one more thing. What is or, one more thing? Parasite drag is equal to induced drag. Those are the all same meaning, okay? You're talking about single spot, minimum drag point, okay? This is going to maximize the endurance. So from here, especially this equation, you can determine the required CL. CL is out of this equation, the relationship. Parasite is equal to induced. This is going to give you the required lift coefficient for minimum, no, actually maximum endurance. This is going to be square root of CDO over K, okay? So let's just plug in drag polar equation into this equation to find out required lift coefficient. So this is 0.018 divided by K is 0.095. This is going to get you lift coefficient required for maximum endurance, 0.435. This is the starting point. And then let's assume lift is approximately weight, fairly close to level flight, because you're trying to maximize the endurance. So flight path angle is close to zero, very, very small flight path angle, okay? If lift is approximately equal to the weight, this is going to be lift coefficient times dynamic pressure times wing area. From here, you can determine the dynamic pressure and then determine the velocity then, okay? So this is like a pattern. So dynamic pressure is the weight divided by lift coefficient and the wing platform area, which let's just plug in. Airplane weight is 5,000 pounds. Lift coefficient required is 0.435. Wing area, 180 feet square given. So dynamic pressure, now we have 63.857, which is pound per feet square, PSF. PSF, okay, standard unit. So this is dynamic pressure you get. This is the 25,000 feet. Let's use the standard atmospheric value of density of 25,000 feet. So this is a standard value of density, which is 0.0010666, which is slugs cubic foot. Okay, standard atmospheric value. Standard ATM. Okay. So from here, you can determine the airspeed, which is 2 times Q over rho. Q, the dynamic pressure we know, this is 63.857 psf divided by density 0.001066 slugs cubic foot, all standard units. So this is going to get you the airspeed 346.13 feet per second. This is the required airspeed at the beginning of this flight for maximum endurance. Emax. This is, by the way, on the initial condition. Do you know why? Because as you continue flying, you keep burning your fuel. Your airplane gets lighter and lighter and lighter. So if airplane gets lighter, what do you need to be doing? You need to accelerate or decelerate in order to maintain the same CL.
Accelerate.
You need to decelerate. You need to fly slower and slower and slower as you get lighter and lighter and lighter. Okay. So this is only initial condition. Okay. So this must be adjusted as you consume your fuel. That's one of the most difficult portion to simulate. In other words, if the fuel consumption is linear, yeah, of course you can use the average method. Sure. But is that the optimum? May not be. May not be. Suppose if you want to fly faster at the very beginning, make your airplane lighter weight, then you really slow down kind of thing. That could maximize the range. Okay. So again, that's where the brigade equation comes into play. So anyways, so starting from here, what do you want? So let's find out the actual endurance for it. Okay. So this is the condition for the maximum endurance. So how much endurance you're going to get out of this condition. So now starting from this condition, lift to drag ratio maximum. Okay. So if you pick up the condition L over D max, this is, by the way, CL over CD, which is maximum value. CL over CD, maximum value. Starting from this condition, okay, note that CD is equal to CDO plus KCL squared. So this is, of course, this is a drag. Okay, and then condition of CDO is KCL. It's going to get you, then plug in to here, CL over CD maximum value. This is going to give you the equation of 1 over 2 times square root K times CDO. Do you remember this equation? Okay. So this is going to basically 1 over 2 square root. K is 0.095 times CDO is 0.018. Okay. This is going to give you a maximum L over D, 12.1. So this is a condition for maximum endurance. Here we go. Then you need to actually take care of, let me change the color here. You need to just actually take care of the TSFC. So TSFC, because usually only given for standard sea level value. TSFC, CT is equal to CT at sea level multiplied by the ratio of speed of sound. So TSFC at the sea level is given by 1.0. The unit is inverse of hour. Let's plug in the speed of sound ratio. Speed of sound at 25,000 feet is 1,016.1 feet per second. You can get this value by square root gamma t. Okay. And then standard sea level speed of sound 1116.2 feet per second. So if you do that, you can come up with the TSFC at the 25,000 feet, which is slightly better than sea level, 0.91 per hour. So if you fly 25,000 feet altitude, of course, you can save your fuel, because it's not sea level. And then let's just plug into the endurance equation. Endurance equation, average value method, okay? W1 initially, this is 5,000 pounds. W2 at the very end, you use up all the fuel. W1 minus weight of the fuel, which is 4,000 pounds. Okay, so this is W1 initial weight. This is W2 final weight. So let's pick up the endurance equation, average method. 1 over CT, CL over CD. Natural log W1 over W2. By the way, actually, this is brigade equation, isn't it? Sorry about that. This is not average method. Brigade equation. Brigade equation. Anyways, because natural log comes in. Of course, in order to maximize this endurance, of course, you have to maximize this CO over CD, right? And which we already know that. This is 12.1. This is the L over D, CO over CD max, okay? So let's just plug in all of those values to determine the maximum endurance, okay? This is 1 over 0.91 per hour. 4.1, this is maximum L over D, multiplied by natural log, initial over final. This is 5,000 pounds over 4,000 pounds. Okay? So if you compute all of those things through it, you are going to have maximum endurance 2.97 hour. This is the max endurance, okay, for this condition. Go ahead, question? No? So this is E max. So obviously, maximum endurance can be reached when you maintain the maximum value of lift to drag ratio, which is essentially minimum drag point, right? This must be max in order to make it range max. Okay. Yeah. So that's the condition for maximum range, minimum drag, maximum lift to drag ratio. Parasite drag is equal to induced drag. Okay. So how about range? Wow. Turbojet, problem of turbojet. It's not really a problem, but the turbojet is different from sailplane. Now, obviously, turbojet, if you want to maintain your engine on, turbojet cannot really slow down just like sailplane. You already have certain value of thrust, okay? So this is as low as you can go. But in order to have a maximum range, so you're talking about R max, range max. What is the condition? Do you remember that? Condition is faster speed, right? Of course. Do you remember this equation? CDO is equal to 3 times KCL squared. Okay. Now, it is always get confused. It's not 3CDO is equal to KCL squared. No, no, no. This is a minimum power required. Okay. So let's be careful about that. I'm probably getting too old, so I can look at those two things. Well, those are the same thing. No, I'm too old because it looks so similar. But those are two different conditions. Minimum power required is much, much slower, even slower than the condition of this. Condition of this is a minimum drag, right? This is even slower. So this is a minimum drag condition. This is even slower speed. That's the minimum power required. Okay. This is slower than this. You can never get this for turbojet, okay, turbofan airplane. You cannot decelerate to this slow speed, okay? So that's the bottom line. If you have a sailplane, of course, you can slow down to this. This is almost the stalling point. So you would basically slow down your airplane almost stalling point. In turbojet, turbofan airplane, you can never do that. So that's the issue of this range. So let's just take a look at range. So out of this condition, so what is the corresponding CL? CL is equal to square root. Okay. CDO over 3 times K, right? So if you plug in this condition, CDO is 0.018, 3 times K is 0.095. So this is going to be So this is going to be 0.251. Oh, 0.251? Yeah, that's a CL, that's why. So let's compare to the CL that you needed for maximum endurance. CL you needed was 0.435 for maximum endurance. Okay. And then maximum range, CL, is much lower value. In other words, you are flying faster speed. You're generating less lift coefficient. Okay. Now, the same thing happened here. Q is equal to, of course, W over CLS, which is, suppose if your weight is 5,000 pounds initially, CL is 0.251, area is 180 feet squared. This is going to get you the dynamic pressure 110.7 PSF for maximum range. Of course, this is much, much faster speed, so higher dynamic pressure. So from here, B infinity, you can get square root 2Q over density rho, again, the same density, 25,000 feet altitude. So 2 times 110.7 PSF divided by 0.001066 rads per cubic foot. You're going to have 455.7 feet per second. So this is much faster airspeed for maximum range, okay? Only initially. Initial airspeed. For maximum range. So if you compare the S value against the airspeed you need for airspeed you need for maximum endurance, which is much faster speed, you're flying faster. Okay. So so what is the actual range then? Okay. So you are going to find out, so how much drag do you have? CD, drag polar equation is CDO plus K times CL squared. We know CDO is 0.018. K is what? 0.095 times CL squared, right? So now CL is 0.251. You just plug it in. Then you are going to have CD 0.024. So this is a CD for your maximum range. Okay. So now you are going to plug into the range equation. Brigade range equation. Do you remember that? This is a turbojet to turbofan brigade range equation. 2 over rho S multiplied by 2 over CT, TSFC. CL to the power of 1/2 divided by CD, weight of power of 1/2 minus weight 2 of the power of 1/2. This is the brigade range equation. You're going to now plug in all of those values. Now, interestingly, okay, the reason why this weird condition comes in, let me just tell you. Where does that weird condition comes into play? If you want to maximize this, this is the condition. That's why. Okay? If you want to maximize this, this is a condition. Okay. All right. So we are going to plug in the value. So square root 2 times 0.001066 rads per cubic foot. Okay. Area is 180 feet squared. Okay. All right. CT is 0.91 per hour. This is 2. CL is 0.251 power of 1/2. CD is 0.024. Initial weight 5,000 pounds to the power of 1/2 minus final weight 4,000 pounds to the power of 1/2. I hope you can do this computation. Now, this is all sorts of units mixed up. So if you compute everything, you are going to probably get, well, of course, you have to convert hour into seconds and all that. Feet is fine, strike is fine, pounds is okay. You're going to get feet result. Now, that feet is going to be converted to the nautical miles. So the result is 653.9 nautical miles. Nautical miles are different from regular mile, okay? 1 nautical miles is equal to 1.1508 regular mile, another statute mile. So let's be careful. So this is the maximum range. This is range maximum because this is maximum. The condition for this is maximum is, mathematically speaking, this is the condition. Here we go. If the CDO is 3 times K times CL squared, in other words, parasite drag is 3 times bigger, what? Yeah, okay. 3 times bigger than induced drag, it is going to optimize this ratio. That is going to give you range maximum. Okay? Cool. Any question here?
What was the answer again?
And the answer. Yeah. 653.9 nautical miles. Let's be careful with the units, okay? If you punch the numbers, you should probably get the feet value. Then feet value converted to miles, miles converted to nautical miles. Okay? Ooh, I spent, well, wait a minute. I have a second page. I didn't use it. Too bad. Well, my solution was concise. That's good. Yeah, I have overflow solution for my master notes. Well, okay, so this page is just your graffiti page. Okay, you can use it for something else. All right, so prepare to be confused. So this is range and endurance for propeller-driven airplane, which is completely different from turbojet turbofan.
Oh my God.
Oh my God, yes. That's right. Okay. So if you are talking about propeller-driven airplane, you're going to basically talk about not the TSFC, but something called brake-specific fuel consumption. BSFC comes into play. It's not the TSFC, it's not the thrust, but the brake-specific fuel consumption. In other words, when you talk about propeller airplane, you're going to talk about power, not the thrust. And also propeller efficiency comes into play. Okay? So you are going to slightly modify the endurance equation. Of course, endurance equation has two variations. One is, of course, average value method. The other one is brigade equation. So 2 equations for endurance, for propeller-driven airplane. And, and here we go. So what actually, okay, maximize your endurance? This is the condition for maximum endurance. Minimum power required. This is different from turbojet turbofan. Do you remember the condition for maximum endurance for turbojet turbofan? Somebody please say something. You don't remember that? Well, we just covered it. Minimum drag, minimum thrust required. That is condition for maximum endurance for turbojet turbofan. This is not. This is a propeller-driven airplane. Maximum endurance. The condition is minimum power required. That means you really, really slow down. Remember that. Slow down. Slow down to maximize your range. Almost stall speed. Okay. This is very, very important concept. Now, if you're thinking about turbojet, turbofan, you cannot do this. Your engine stalls out before your airplane stalls. That's what it is. You cannot slow down this much. Okay. Now, so you have a two variation of equation. One is the average value method endurance. This is the brigade equation for endurance. Okay. Let's take a look at the range equation. Range equation is, of course, it's a kind of similar but quite different. Okay. So here is the range. Of course, the range is, yeah. Okay. Next page. So obviously the range is endurance multiplied by the airspeed you fly. So flight airspeed comes into play. So if you multiply the endurance equation with the B infinity, this is the range for average value method. This is the range for brigade range equation. Now, what is the condition for maximum range? Interestingly, what is the condition for maximum range for propeller-driven airplane? Quite important. This is different from turbojet, turbofan. This is the condition. What is this? So obviously, lowest drag, optimum lift to drag ratio, parasite is equal to induced. This is the condition for maximum range. Then you go like, wait a sec. Isn't this the condition for maximum endurance for turbojet, turbofan? No. This is propeller-driven airplane, so it's not. It's like, hey, isn't that? So I'm confused completely. So turbojet, turbofan, this is the condition for maximum endurance. But the propeller-driven airplane, this is a maximum range, right?
Wait, what?
Okay, so you're confused. So let's just take a look at summary. This is much better. So I came up with a range and endurance summary here. This is something I added last semester. Last semester's notes didn't have this. I just added. This is something new for you. Last semester, students took my class. They had no clue about this.
We're taking off.
Oh, it's going to close again. And it's okay. So let's just summarize range and endurance, whole thing. Okay. So we looked at the three different types of airplanes. Do you remember that? We started with a sailplane. Okay. So this is a sailplane, no engine. So sailplane's maximum endurance is essentially the condition for minimum sink rate. Okay. The condition for that is 3 times CDO is equal to K times CO squared. This is minimum power required point, even though sailplane doesn't have any power plant. So it's kind of odd to say this is the condition for minimum power required. What kind of power are you talking about? There's no power for the sailplane. Okay? But it is kind of making sense right now, because after we talk about all of those things. So what is the maximum range for sailplane? That is essentially best glide ratio. Condition is minimum thrust required, or simply put, minimum drag point. If you keep flying your sailplane for the condition for minimum drag or maximum lift to drag ratio, or the condition for parasite is equal to induced drag coefficient, it is going to maximize the range. Maximum range means best glide ratio for sailplane. Okay. So this is the condition that, suppose even if you're flying turbojet to turbofan, you just cut off the engine, turn it into sailplane. This is the condition. All of a sudden, conditions changed. Okay. So now let's just take a look at the turbojet to turbofan. Of course, the engine comes into play. Jet engine is not very good for low speed. In other words, it's going to stall if you slow down too much. So there's a limitation for how slow you can fly for the turbojet to turbofan airplanes. Okay. So maximum endurance is as slow you can fly as humanly possible if you have turbojet turbofan airplane. This is a condition for minimum thrust required, of course. Yeah, right? Because when you design turbojet turbofan airplane, minimum thrust required is something coming into play. That's how much you can slow down this airplane. If you slow down more, you're going to stall your engine. You can't fly like that. If you want to fly like that, just to cut off the engine, make it sailplane. Sure. Then all of a sudden you switch the equation from here to here, right? So this is the condition for maximum endurance. This is the slowest possible speed you can fly with jet engine powered on. Does it make sense? Okay, so that's why this is the condition. So this is equal to that. Yeah, that's right. Yeah, that's right. Because this is the slowest possible speed. And then in order to maximize the range, you want to fly faster. You want to fly faster because the range comes in endurance times velocity. So velocity is going to be much faster. So this is the condition for the maximum range. CDO is equal to 3 times KCO squared. Okay, this is much faster speed. Okay. Now, if you talk about propeller-driven airplane, this is, wait a minute, exactly the same as sailplane. Right? So this is something I came up after I taught last semester. I realized, wait a second. So I came up with this summary made up by myself because no one else actually summarized like this, including those textbook authors of Air Force Academy. They don't teach like this because I'm not the performance guy. Unless somebody summarized like this, I can never understand. You know, I keep confusing. I was confused up until like last semester. Ever since I took this class when I was undergrad student, I didn't understand what the teacher was talking about. So now so I feel comfortable. So this is a big picture, isn't it? Right. So what actually causing those differences? This is quite important. Okay, let me just zoom in. So what makes the difference between endurance and range? What's the difference? Okay, for an airplane, the longest endurance is achieved near the airplane stall speed. You have to slow down as much as you can to make maximum endurance. That's what it is. You don't care about how long you can fly. You want to stay up in air as long as possible as the time is concerned, okay? So the speed at which it is just able to maintain its altitude, that's called maximum endurance. At this speed, the wing is just supporting its weight of the airplane, okay? So the power that the engine needs to generate to push the airplane forward is lowest. So this is minimum power required, even though sailplane doesn't have a power plant, so it's weird to say. But same as propeller-driven airplane, sailplane equation for minimum sink rate is the exact same equation of maximum endurance for propeller-driven airplane. Make sense? So how about range? Flying an airplane at the cruising speed. Cruising speed is not the minimum speed. Requires more power, obviously, but again, you are pushing your airplane for more longer distance. So it is going to maximize the range, okay? So that's big difference. So if you fly near stall speed, you're not going to maximize your range. You have to fly faster, okay? So the condition here is a minimum thrust required or minimum drag condition. This is going to optimize your range here and here. So this is essentially best drag ratio for sailplane. The same equation applies to propeller-driven airplane. The only exception for turbojet turbofan is, of course, the jet engine cannot slow down that much. Okay. But the great thing about that is you can fly much faster for turbojet, turbofan. So you can actually optimize your range. Okay. So this is very, very confusing subject, range and endurance. Very confusing. It's going to be guaranteed to show up on exam 2. Okay. All right. Guaranteed. I can say right here, right now, I'm going to give you at least one problem dealing with range and endurance. Too bad. So you have to understand. Okay. All right. So next, just to stop here today. So next class, actually next week. Okay. We are going to finish up Unit C2. We're going to get into Unit C3. Unit C3 is takeoff and landing and turn. Those are the performance. Unit C3, we're going to take a look at what's the takeoff distance, landing distance, what's the constraint, and also turning radius and then vertical and horizontal turns for the airplane. Of course, the
good stuff.
yeah, that's a good step. It's basically how strong your airplane comes into play. Load factor and all that. Okay. So have a great weekend. All right. See you guys next week. All right. Have a great weekend.
So tomorrow.
Do you have any questions, Jordan?
Probably same, yeah, because
Okay. Let me just stop recording.
sorry.